Kamampati, who has done some amazing work in human-aware AI systems, and in particular, the explainability thereof. So Dr. Kamampati is a professor at Arizona State University in the School of Computing and Augmented Intelligence. And he has many, many accolades. Like among the most notable, he's a fellow of AAAI, AAAS, HCM. He was a president of AAAI. And so his work is really interesting, and I highly encourage everyone to check it out. So please take it away, Ra.
Okay, can you see my slide then?
Yep, all good.
Okay, great. Okay, so let's get started. Okay, thank you folks for waking up early in the morning. It's still late in the evening for me. My whole day is over, but I'm behind you. So as Joseph said, I will be talking about symbolic mental models as lingua franca for supporting explainable and advisable human AI teaming. I noticed there are two firsts there. I don't know why, but anyway. So I do want to point out, I do want to say that I do wish that I was actually in person. You know, if I was in person, maybe I would have just been walking around Kyoto rather than be in the workshop. That's a different story. But the last time I was in Kyoto was 25 years back for Ichikai in 1997, and I really loved the city. So I miss being there in person. My research background is explainable human AI interaction. And I'll talk about the settings that we look at, etc., in a minute, but our setting involves typically collaborative problem solving, where AI agents provide decision support to the human users in the context typically of explicit knowledge sequential decision making. So think, if from the robotic side, think task planning first. Although the second part of my talk, I will look at how to look at the tacit parts, for example, the robot walking sorts of things. So in general, I think this distinction between tacit and explicit tasks is something that is very useful to keep in mind for people interested in human AI interaction. I know that for example, some of the pictures that earlier on Joseph was showing are basically tacit knowledge, interactions. We sort of know that what we have to do when we are passing by each other and so on. But there's also equally specific goals that I might express to my assistant and also be surprised at their behavior and ask for explanations. And those are typically the explicit knowledge parts. We develop frameworks for proactive explanations based on what I would call model reconciliation, as well as foil-based explanations, such as why did you do this? Why not do a very different decision, for example? And we typically, one of the other things is that, I tend to say that if you are in human AI or human robot interaction, and if you haven't heard about IRB, then you really don't care about human robot interaction or human AI interaction, because that's the only way you can actually study how these interactions work with humans in the loop. And so we do, we have demonstrated the effectiveness of the things that we do with respect to that sort of human subject studies. So that's my group there, some of the students whose work I'll be talking about. And there's a book on explainable human AI interaction, a planning perspective, that I'll have a chance to talk about in a minute. So let me get started. So what does it take for an AI agent to show explainable behavior in the presence of human agents? And my simple answer, and this is a slide that I show all along, it's not just made for this particular workshop, by the way, is managing mental models. Those of you who know Salient test, for example, know that essentially the way we deal with others is by modeling their mental states, and based on that, structuring our interactions. So managing mental models winds up becoming very important, and that's sort of the underlying theme of our entire work. And the talk itself is structured into two parts. Part one is actually using mental models for explainable behavior typically in the context of explicit knowledge tasks. As I said, think task planning. There I'll talk about what we call our three-model framework, the model that the robot has of the task, the model that the human has of the tasks, as well as the model that human has of the robots model, the estimate that the human has of the robots model. And typically this MRH is the one that winds up becoming very important in the AI agent or the robot showing behavior that is not too surprising to the human, and also providing explanations with respect to that. We'll talk about in a minute. And so explicability winds up saying that the robot should conform to what the human thinks it is actually capable of. And explanation says the robot actually tries to get the human's approximate model of its capabilities to be more in line with its actual capabilities and constraints. And then we have done work in this direction, and then bunches of extensions about how to handle different kinds of explanatory questions, different kinds of abstractions of the explanations, how to handle multiple humans, and so on and so forth. And this stuff is the first part I'll talk about, and that's actually in sort of written up in a book that just came out in the beginning of this year. And then the second part, what I want to talk about is what happens if you actually cannot, it's not an explicit knowledge task, or at least from the AI agent's perspective, it is a inscrutable model that it's using for its reasoning. And the stance we take is, I don't really care what your reasoning is, the AI agent's reasoning is based on, but if you are talking to the humans, if you're trying to explain to them, you better explain in terms that make sense to humans. So that means you have to provide a symbolic interface through which you both provide explanations as well as take advice. So if the humans have advice as to how you should behave, they would be giving it in terms that are making most sense to them. And so that would again be oftentimes, definitely involve symbolic components. So those are the two parts I'm going to talk about. It's approximately half and half, hopefully. So let's get into the first part. So the three models that I mentioned essentially, start with, if the robot, or if the AI agent is the only thing in the world, it has its model of the task, its own goals, its own initial constraints, and then it's basically trying to come up with a policy or a plan that will achieve those state of affairs. This is typically the planning of any kind, whether you're based on stochastic dynamics or deterministic dynamics. This is basically the planning of any kind. But the moment there is a human in the loop, suddenly you now have the human has their own model of the task. So they may, for example, assume the same dynamics of the environment, or they might actually have different dynamics that they assume that the environment has, and the expectations that the robot and the human has about the model the environment might be different. And then certainly the humans will have different goals. For example, in addition to their common goals, they might have specific things that they would want to achieve. And so the M of H is the human's model. And typically what has been called human-robot interaction for the longest time has been for the robot to get an estimate of this M of H. So what I would call the robot essentially has to have an approximation MHR, which is essentially its estimate of what the human's model of the task is, and it can use that to either anticipate what the human might be doing, to provide assistance to the human, as well as at least get out of the way. In fact, much of the work that is still being done in the so-called cooperative AI typically goes at this level. So if you look at something like the overcooked domain, in a sense, you are trying to kind of at least get out of the way of the human chef, if you are a robot, for example, and then maybe provide assistance. The third level, that's actually kind of more of importance as far as explicable behavior and explanations are concerned, is that the moment humans are in the loop, they will have estimations of the robot's mental model. The interesting part about the mental modeling is AI systems have to make an effort to generate mental models. Humans cannot help but make mental models. We essentially ascribe mental models to even inanimate things, right? And basically this has been very well known in psychology. So the moment humans are in the loop, they have an approximation of what they think are the robots' model of the environment, which you will say MRH. And it turns out this MRH becomes very critical for the robot to show behavior that the human expects, or to at least tell them why its behavior is different from what they would expect based on MRH. So MRH is essentially what the humans estimating the robot's task model is. And the robot has to kind of get an estimate of this and use it in its behavior so that the human should not be surprised and should at least understand why it is doing the decisions it's making. So if there's any question for explain your decision, it is with respect to MRH that it's going to be explaining this. It's worth noticing that I'll give you examples of these sorts of models in concrete scenarios, but it's worth noticing that MHR and MRH are essentially expectations on the models. They are not actual environment models themselves, so they don't actually have to be executable. So that means you tend to have a lot more freedom on these sorts of models. So the interesting question is, what happens if there are model differences? What if, in fact, MRH, that the human expects, human's expectations of the robot model, is quite different from actual robot's model, MR? So to the extent MRH is different from MR, the behavior that the robot shows, and when I say model, by the way, it's not just the dynamics, it's also the goals that the robot has, the constraints that the robot has, etc. When it's basically, if it's just optimizing with respect to MR, and that would wind up being inconsistent with what the human expects, so you will wind up seeing inexplicable behavior from the human side. And then the robot then has two options. One is either conform to the expectations that the humans have, that means actually behave according to MRH rather than according to MR. So do what people expect you rather than do what you want to do, or provide explanations. So that is, resolve any perceived suboptimality by telling the human, this is the way your expectation, MRH, is wrong compared to the actual MR, my model. So this second part is explanation. The first part is explicable behavior. And then both can be used. And in fact, if you consider something like this scenario where you have a map of the environment that is known upfront to both the human commander, let's say, and the robot, and so this map is known upfront, so they start with that as the environment model. However, the robot is actually in the real world, and so it might actually see that the map is impassable in certain places. For example, this could be a search and rescue scenario. There are rubble in some paths, and so certain paths become impassable, because of which the maps actually are different now. The MR winds up becoming different from MRH, and that will change the human's expectation. That will make the robot's behavior be different from what the humans would expect. And so I'll show you two examples here. So in this particular case, given there's a particular place that the robot has to go, it turns out that the shortest path is through this particular, corridor, and then we put a fake obstacle there. So essentially the robot either if it has to go through the shortest path, it has to be explicable, then it needs to do the business of actually removing the rubble from there and then pass through that path. Now, this is an interesting point that to be explicable, essentially, the robot had to do additional work. And this could be reasonable, in particular in certain critical scenarios where the humans are only waiting for the robot in one particular exit. And you can't just say, I'll go to a different exit just because this exit is closed if you don't have communication with them. So sometimes explicability is actually very much required. And so in sense, generating these kinds of explicable plans requires minimizing not just your cost, but coming up with an optimal policy for yourself, but also making your policy be as close to what would be expected, given humans' MRH. That basically means you want to, make a policy that's closer to what humans expect. So that means there's the distance between the policy you are actually using and what humans are expecting should be minimized to. And this is a more complex, cost minimization. And sometimes it could actually make the robot's life much harder in terms of the, resource costs and so on. The other possibility is for the robot to just say, to heck with it, I'm going to do what is optimal for me. In this particular example, we'll see that the robot will actually go through the second best path, which becomes the best path right now, because one of the original best path is essentially there are obstacles there, so it cannot be passed. It's become impossible. And so in that case, you do this, but you realize that the robot realizes that the humans would be surprised at your behavior. And so you kind of give an explanation up front saying, change your model MRH, such that, which actually take into account the information that this particular path has just become, impassable. And once the MRH changes, then the human's expectation of what the best path would coincide with, hopefully, what the robot is doing. And so they would be happy. So explanations will then become model reconciliation. So the human, what are we explaining? We're explaining the AI agent is explaining to the humans how to change their MRH representation. And we, much of this discussion, I'm doing it at without actually saying which type of models, MR and MH, which representations I'm using. That's partly because actually these are general enough. But if you're thinking of something like actions with preconditions and effects, then humans essentially might have missing preconditions or additional effects or missing effects for the same actions that the robot has, in its environment. And so the explanation process is changing this model such that the models become aligned. So if in fact MRH is the same as MR, then this is kumbaya. Essentially, whatever the robot is doing is exactly what the humans would be expecting, and there would be no questions asked anymore. Computing these kinds of explanations is essentially search in the space of models. And so for something like PDL models, which is like this action precondition effect models, it would essentially be a search in, starting from MR and going towards MRH, or starting from MRH and going towards MR, in terms of deciding what preconditions and effects have to be changed such that for the particular problem at hand, there is no confusion from the human side. And it turns out that as you're hearing this, you might just say, why not just give your entire MR to the human? And that would make the explanation be too large most of the time, too large and unwieldy. Typically, if somebody asks us, why are we doing what we are doing? We can always just say, here's my brain, take it. If you put it on your head, you would know why I'm doing what I'm doing. That's just an extremely inefficient way to provide explanations. We tend to get them in alignment with our constraints with respect to the current problem. And that's where that search in the model space is happening. And so in the context of that example that I've shown you, so the robot notices that this particular path is closed. So it actually takes the better path with the second best path. And then it's yelling. If I had the audio on, it was yelling that the path, change the model MRH so that the path of, that particular path is closed. And the moment the human does that, then their inference will also tell them that the robot would be expected to take the next optimal path, which is this. So that's basically the simplest form of explanation. So one question here would be, how do AI agents get the human's mental model? This is one of the big points in the workshop here too. It's worth noticing that in some cases, such as the USAR scenario that I just mentioned, you might have started with a shared map. So human and the AI agent will start with the same shared model. And then the model drifts because the AI agent is actually getting more information about the environment that the human doesn't know. Or, for example, the human can have new goals, in which case they have to get them, a robot to understand that. Even if the robot doesn't know the model MRH with certainty to begin with, it can reason with multiple possible models. We have done work showing how actually a robot can provide explanations not knowing which of the 5 different models the human might have. So you provide an explanation that sort of makes sense for either all the models or conditionally for one of the models that you expect is the right one. And again, this is not surprising if you look at some of the work that's been done in the cooperative here from the RL side. There's been some work that basically, I think in the overcooked domain, people try to train a robot on all possible models of the human, such that it will cooperate or at least avoid getting into the way of every possible type of human chef. This way, hopefully, it will then be able to, in real world, it needs to just figure out which particular model it is likely to be in the context of and sort of avoid getting in the way there. So that's the kind of thing that we can do here too. That's actually, we have done this probably earlier in 2018. In other cases, we do actually have to learn the mental model, and then that would have to be learned from the traces of the behavior, prior traces of the behavior. We have done work on those directions too. And then one other final thing I want to mention here is that if you have the model, the description was made in terms of an explicit MRH and explicit MR, but if you are modeling the human, you don't necessarily have to have MRH. You can do model-free explanations, model-free explicability, where instead of learning the model, you just learn the human expectations from experience and use that as a stand-in in your explicability or explanation generation. So in fact, way back in 2017, we were talking about how to do model-free explicability, where essentially, instead of learning MRH, you learn the human preferences that would be the footprint of that MRH. And then we can also do model-free explanations or model-free model reconciliation. That was a paper in HKI 2019. And so the general idea here, in this part of the talk is that the humans and the robot essentially go through this loop. The AI agent and the human are going through this loop. The AI agent is sort of starting with an initial estimate of MRH, either because it's been initialized that way or it learned from the previous interactions. And then there's a kind of an ongoing loop where it's either following the model that it thinks the human has of it, which is MRH. That's where notions that I have talked about, explicability, as well as other notions that other people have talked about, such as predictability, come in. And then the other would be model communication, where the AI agent tries to correct MRH. That's where the explanation, which I talked about here, as well as things like legibility, as well as environmental design, come in. And so this is like the bigger picture of AI agent interacting with humans, especially in these sort of explicit knowledge domains. And then we also can point out there's some work that we've done showing that the kind of explanations that we generate are, inconsistent with the psychological theories of how humans ask for explanations and humans receive explanations. This is a busy slide. I don't have the time to go through it piece by piece, but hopefully you can look at it in the slides later on. We have done several extensions of this general type of explicability and explanation, including supporting reconciliation and non-PDL style, non-action precondition effect style settings, providing other types of interpretable behavior, and also in the examples that I showed, the robot proactively provides the explanation because it realizes that the human would be surprised by its behavior. But typically, a much smarter idea is to wait for the humans to ask questions. That would be basically file-based explanations. And we've done lots of work in waiting for the human to ask, why did you do this decision as against this other decision? And then provide an explanation that sort of ineffectively changes the MRH to make it clear to them that the choice that they're suggesting is actually infeasible given the robot's model. And then you can also handle multiple human agents, as I mentioned earlier. And then one of the other things is this is all connected to trust as well as deception. If you have mental models, you can use it to cooperate as well as deceive or lie. And it's the same thing that can be used either as a tool or a weapon, and you can't get away from it. And so we actually have done work on showing how mental models can be used in lying and whether or not people would be at least happy with being told white lies by robots, for example, and how to use mental modeling for obfuscation and deception, where essentially you are making, you, the AI agent, is leveraging the differences between MR and MRH to actually signal a different behavior than what the actual behavior what your intentions are. So it kind of camouflages your intentions. And then finally, essentially, if you do what people expect you to do, they tend to trust you, and so you can sort of increase the trust over a over a longitudinal interaction by sort of doing what people are expecting, and then that sort of can be used. That once you have more trust, then people are likely to actually look the other way and let you live your way. This is basically what happens in teams, So trust becomes very much connected. So we don't ask explanations for people whom we trust, even if their behavior is surprising to us. We'll just assume, I'm sure they have a reason. And so this is something that is going to be happening even with the human AI interactions. This much of all this stuff has actually been written up. There's several papers, but we also did a monograph on explainable human AI interaction. It talks about measures of interpretability, the explicability, explanations, and other types of interpretability restrictions, and also how do you get the mental models, and also this idea of being partly explicable and partly providing explanations. That means I'll go halfway to make my behavior be consistent with what you're expecting. For the rest, I change your mental model of what you are expecting of me, so that MRH becomes more inconsistent with MR. And so we did this thing, and so and then we talk about the kinds of the applications that we look at in this work. So that's sort of the first part. As I said, in some sense, it's been completed just about a year back, and then this book has actually come out. And so I just wanted to give you the bigger direction of our group's work in providing these kinds of explicability and explanation and explainable interaction. The part that I want to talk about now is more recent, which is doing the same sort of explainable behavior, but also without actually assuming that this is an explicit knowledge task or that there is any shared vocabulary between the humans and machines. The one point I want you to understand is that even if, in fact, there is shared vocabulary, which is sort of what we expected in all the slides up until now, providing explanation is still a challenging task because it actually involves search in the space of models, and providing explicability is also challenging because you are also trying to be optimal with respect to not just your own constraints, but also with respect to the constraints that the humans, possibly wrong model of your capabilities are imposing on your behavior. So keeping that in mind, now if you add on to it, the possibility that, in fact, there is not much of a common vocabulary between what the robot's internal reasoning is and what the humans inference on the task is. This could very well happen, especially as we get into situations where you have massive systems that are essentially inscrutable. The only thing that's common between the human and the machine is the actions being done. So only the behavior is seen. And so how do you provide explanations in those cases? And there, the argument that we have made, and in fact, there was a Blue Sky paper in IIII this year, is showing that, is basically arguing that symbols should be used as a lingua franca for explainable and advisable human AI interaction. And so even if, in fact, the machine, even if the AI, the robot is not actually using any kind of a symbolic reasoning, the explanations have to be provided in terms that make sense to the human, so that they have to be post-hoc explanations are reconstructed in terms of symbolic vocabulary. And then similarly, the robot should be able to be advisable, and the advise would be typically in symbolic terms. At least one of the modalities will be symbolic terms. It's not always the case that humans are just going to show some demonstrations and say, do it this way. We actually use language. And so the machines have to be able to use that advice and use that to change their behavior. So that's something that I want to talk about, some of the issues there. So in the context of explanations in the absence of shared vocabulary, in some sense, this is what has been looked at a lot more in the quote unquote explainable machine learning community. And typically, their approaches are suboptimal from my perspective, as I'll point out now, because they sort of tend to assume that the lowest common denominator between the human and the machine is just the substrate that they both are looking at. So, for example, if I'm looking at some images, then I might ask, apparently, in the image, why is this a dog? Or why do you think this one is a, let's say, Siberian Husky? And the machine essentially shows the pixels, the saliency regions have become like a way of talking about explanations. The pixels that seem to have played bigger part in its decision, in its basically classification decision, right? So that's something that you're aware of. But it turns out that pixel-based, the saliency region-based explanations are essentially the most primitive kinds of explanations, and humans evolved basically to, if we keep doing pointing, it's actually impossible to do for most of the sequential decision-making problems. For example, if you ask me, Ra, why are you giving the talk on the Zoom as against being in the room, I need to kind of provide you some sort of a video of my life and its constraints in the recent past, which will try to provide you an explanation as to why I am not there in Kyoto and why I'm on the Zoom. And that is essentially doing saliency regions over sort of a video, or what I would generally call space-time signal tubes. And if we had to provide explanations to each other that way, we would basically have given up talking to each other. So in some sense, and I actually don't know too many people, humans, who ask, why do you think something is a dog to other humans? So I'm not quite sure you're going to do that to your AI agent unless you're actually trying to debug the AI agent as against being as a team member with the AI agent. And as I point out in this, this adversarial example situations, right? What possible saliency region could you give as to why the right-hand side school bus is an ostrich? It would be some arbitrary set of pixels which have no meaning whatsoever to humans in the loop. And so that is something that I want you to keep in mind. Explainable ML sort of, and the saliency regions, other people have also started getting sour with it, but I think it's just saliency regions are not a great way to provide explanations between agents. So pointing explanations are actually, as I mentioned, hard to comprehend. To some extent, I might argue that that humans developed language just so that they didn't have to point to these imagined space-time signal tubes. At least now I have a video. I can send you some kind of a video of my life. But if we were just a couple of cave people, what were we going to talk about as to why I did this decision as against that other decision? We had to have abstractions, and essentially symbolic abstractions, and language may well have evolved that way. So this sort of approach obviously works for explicit knowledge tasks, but one of the most interesting things, and I'll bring this up later on too, is that our language instinct symbolic instinct is so high that we use terms even for fully tacit knowledge behaviors. For those of you who are into like basketball, for example, you just make up, we have these words, like these phrases like pick and roll, the concepts like pick and roll, which essentially has a grounding over the space-time tubes of, players, dribbling the ball on the court, for example. So in general, we want to support these kinds of symbolic interface layers to provide explanations as well as take advice. So that's basically the point of our Blue Sky paper, as well as some of the papers that I'll be mentioning in a minute. But before I go into that, since I'm allowing machines to be basically doing inscrutable reasoning, I don't really care whether they're using symbolic means in their own reasoning or not. I only want them to provide explanations and take advice through the symbolic interface. And this is different from the normal trend in neurosymbolic AI, which tends to be about internal symbolic reasoning, that there is this argument that without internal symbolic reasoning, you may not reach human level AI. I don't have a stand on it. I don't know whether that's true or not. And it's in fact, pretty hard to prove one way or other, as of now at any rate. But for sure, I think that if you have AI systems basically coexisting with humans, you don't expect humans to be dancing around trying to explain, miming their preferences to the machines. It just makes no sense. So we essentially want AI systems to grow a symbolic interface that through which they can actually provide explanations as well as take advice. So this is the sort of external neurosymbolic communication interface. It's a different motivation for neurosymbolic. Except, the machine can do whatever reasoning it wants, but it should provide post hoc explanations that are symbolic in nature. And I want to tell you how that can be done in a couple of cases. So the use case for the symbolic layer, of course, is the AI agent may well be doing, whichever your favorite, reasoning mechanism, like pixel-based deep reinforcement learning or some other method, a RAM state-based reasoning in, for example, Atari games. But the humans tend to think of the same pictures in terms of objects and their relations. And when they ask a question as to why did you do this particular decision, the question tends to be in symbolic terms. And the answer should be in symbolic terms too. So in essence, the AI system has to provide a local symbolic model, post hoc symbolic model with respect to which it explains its decision. And the idea we use, and this is actually a paper in ICLAIR this year, is basically we start with the assumption that there are some user-specified concepts. So that means there's some shared vocabulary, some vocabulary that the machine knows the human understands. It may or may not be shared in the beginning. And then since the human understands this vocabulary, then the machine has to make sure that it finds grounding for them and it knows how to use those words. And then when the user raises a foil, such as why didn't you use a particular alternate plan, foil-based explanations are very common in explainable AI literature. The machine, in this particular case, we are looking at an Atari game scenario where in essence the machine may well be doing its behavior. In this case, I think it's doing in the RAM state, but it could also have been doing in the pixel space. But the humans are thinking in terms of ladders and people and obstacles. So their questions can be in those terms. And you want the explanation to be also in those terms. So the machine essentially, even if it has something like a saliency explanation that it computed, it essentially has to approximate that in terms of the concepts that essentially will correspond, which cover that saliency region. Except since I'm talking about actually sequential decisions, you are learning a local PDDL model. What we wind up doing is learn a local action precondition effect model. And then at the point where the human is questioning our decision, and then the file provided by the user is simulated to identify the failure points in your own model. The machine does that. And then it tries to explain that failure points in terms of the action preconditions and effects that it learns locally at that point of time. So those of you who might be familiar with the old work on things like LIME, which provided a local linear approximation to some highly nonlinear model, here we are finding local symbolic approximations to some inscrutable model. That's what we wind up doing. And in doing this, we can also keep track of the machine. Since it's a post hoc explanation, the machine can also keep track of how much of a confidence it has in the explanation that it's providing to the human in terms of whether the explanation actually captures, for example, its internal reasons, probably in terms of this, saliency maps and so on. And that confidence level can be used to ensure that humans, to ensure if the machine is well behaved, it can use that to ensure that people don't put over trust in the machine's decisions. This is something that we can do too. So we actually, done experiments to show that, compared to saliency-based explanations in this particular domain, in this kind of domain, people do like, receiving symbolic explanations. So the same idea can be used. The dual of this is accepting advice. So essentially, the symbolic interface will also allow machines to accept advice. Accepting advice is a way of learning preferences and following preferences. You don't have to always learn. People can actually tell you what their preferences are. Please do this particular goal. And then these kinds of advice will again be in symbolic terms. And if you are doing your reasoning in pixel space, then how do you ensure that you can still accept the symbolic information? So we have a paper in NeurIPS last year. It's a spotlight paper on in a deep reinforcement learning scenario, when humans are actually providing advice on the right dynamics, for example, for the machine, so to improve its understanding of the environment, to, in the beginning case, actually to increase the speed of convergence, but it can also be used for generally just giving additional preferences by the humans. What we wind up doing is we allow humans to provide, so humans will say, in this particular state, do this action, the human in the loop reinforcement learning, typically once in a while, the machine will ask, I'm about to do this action in this state, is this okay with you? Is this okay? And the human might say, no, this is a different action should be done. And the reason you should do this different action is because, for example, there's a stop sign, so you should brake, for example. And that the stop sign, is in terms of concepts that make sense to the human, in terms of objects and relationships. And the machine will then convert these into pixel space annotations and then use it at the pixel level, because it's mostly doing its reasoning at the pixel space, as a, deep reinforcement learner. And if you do this, and in fact, there are certain things, since as long as you're stuck in the pixel space, if the human provided an explanation, you can also augment that explanation and say, as long as the particular objects they mentioned are kept constant, the rest of the image can be modified. So you can do Gaussian blur or something, and it would still the decisions should still remain the same as the one that the human suggested. So you're actually, one of the big issues in the humans being advisory role is how to reduce the sample complexity in terms of the number of times you're asking humans for the advice. And this augmentation can be used to essentially provide a leverage for one single example. You're actually expanding it to multiple examples that are still equally useful for the machine in improving its convergence speed. So again, we have shown that in fact this improves performance quite significantly, in the convergence speed. But the general bigger point for me is that you can do this in the symbolic terms, and because of which, so humans are still doing the explanations in symbolic terms rather than talk in terms of saliency regions. This becomes even more important if, in fact, the human preferences, for example, typically the preferences are on trajectories, preferences are on space-time tubes. And if the humans are giving preferences on how to walk, for example, which is something like for reasons unknown to me, very popular in the robotic, preference learning communities. So there are like two extremes. One is like basically trying to learn from the trajectory comparisons, pairwise trajectory comparisons. And that is so inefficient that it's almost people actually do that kind of a work by putting a simulator for the human. Just as the environment simulator makes sure that the robot doesn't die, if the environment is non-ergodic, human simulator makes sure that the humans don't die of boredom in giving all these many trajectory comparisons. What we would like to do is, normally the way we tell each other is, don't walk so fast, or walk more softly. So these are essentially symbolic terms which are sort of relative attributes over these trajectories. And we can learn the grounding of the relative attributes and use that to improve the preference learning. So there is work that's actually being presented. This will be presented in the New Rips Hill workshop this year on how you can learn that sort of the relative behavioral attribute grounding and use that as an efficient way to get human feedback on even actual preferences over trajectories rather than preferences over single state action decisions, which are actually, trajectories basically correspond to space-time tubes. So that's the other part. And then we have done other work. There's like an ICML piece which allows humans to have provided their model of how the task has to be done in potentially incomplete way, and let the RL system still try to use this incomplete model and try to actually make a behavior that sort of corresponds to, in our particular language, the landmarks of the high-level plan that correspond to this, incomplete model. And then what we wind up doing is we try to learn a diverse set of skills to reach these landmarks and then combine, members of these to actually come up with a, successful behavior. Once again, this winds up any kind of a direction for a deep reinforcement learning system winds up being extremely useful. So this sort of thing winds up being a faster way for the humans to have provided canned preference knowledge about what they want them to do, even if it's in fact, figuring out low-level details during the RL time. Once again, experimental evaluations show, significant improvements, and there's a paper in ICML on that. One last thing here is this sort of a thing can also be used if what you're doing is understanding the human's demonstrations, not humans, verbal prescriptions, verbal preferences. So one of the things, if any of you have played dumb charades, where you mime a movie name or something, that the reason we are actually able to do demonstration of this miming demonstration, we are able to parse it, is because we know that there is some symbols that are corresponding to the actual miming that you're doing, the demonstration you're doing. And the fact that you are aware of that allows you to do parsing of the demonstrations much faster. There is actually a paper in this year's III on how the very potential knowledge of the symbols that make sense to the humans allows the robot to, or the AI system to parse the demonstrations much more clearly. So this part actually, this idea of generating a symbolic interface, I have given you some specific papers, most recent ones, but in the Blue Sky paper, we also talk about the open research challenges in making AI systems have these kinds of symbolic interfaces. And that involves essentially collecting the initial concept set, grounding the concept set, as well as, most importantly, vocabulary expansion. Collecting and grounding concept sets, these are things that actually get amortized. If you think of something like a scene graph, essentially it is already has collected and grounded concepts that make sense to humans. When a machine actually looks at the scene graph of a scene, it already is parsing it in terms that make sense to the humans rather than necessarily from a pixel level. And then the vocabulary expansion becomes very interesting. That it has two different aspects. One is the machine realizing that the vocabulary that human has provided upfront is not good enough to actually provide a good explanation for its decision. So that it can do by keeping track of the explanation accuracy, explanation confidence that I mentioned earlier. And if the confidence is too low, that can be used to increase to kind of start an interactive dialogue to increase the vocabulary size from the human. That is, these are vocabulary items that humans understand. The machine did not have grounding for them. So this will then expand more common ground, and then you can do more things with that. The other option would be that the machine has basically trying to explain something for which humans don't have words at all. This could happen in the foreseeable future. In fact, that 37th move of AlphaGo, which people keep saying, we don't know why it made sense. None of the humans would have made that move. Typically, when people say that a move doesn't make sense in Go, it's because they don't have a clean symbolic explanation as to when that kind of a move would make sense, given the symbolic view of the board. And at that point of time, the machine may have to help the humans come up with new kinds of concepts with respect to which these decisions can be explained. This is all, of course, Blue Sky research. And so these are research challenges that you can look at. In summary, and I think looks like for the first time in my life, I'm actually ending on time. In summary, I again basically talked about some of the work that we're doing in explainable human AI interaction in the context of both the work that we have completed in terms of the explicit task models and this three-model theory of explanations and explicability, and also what should that sort of work do when you wind up having not enough common vocabulary. So there is no actual common ground, but then you establish the common ground and use that to provide explanations and show explicable behavior. I'll stop here. If there's any time, I'll take questions. Otherwise, thanks for your attention. Are we there?
I don't know if the clapping came through, but thank you for the great talk. That was awesome. Yeah, if anyone here, we have microphone in a room. So if anyone here has questions, feel free. Same with people on a Zoom, like by all means, if you have questions, you can either raise your hand and speak or just post it in chat and then we'll take it. I will go ahead and start off then because I was taking some questions of my own.
Okay.
So this is really interesting. I didn't realize you were doing like post hoc labeling of symbols and stuff. One of the challenges I think that kind of comes with that is trying to build like a large curriculum with these symbols, right? So if one person might look at something to robot data pattern and say, okay, I'm going to post hoc label it this kind of symbol, but somebody else might label it something else, right? Like there could be disagreements. How do you think we can address this to actually build something like large scale?
No, so there is this aspect. I mean, first of all, there is, in terms of symbols and their grounding, essentially, I think that there is obviously enough commonality that we can get by, but there's also variation. So the one question that I did not specifically touch on is, are the symbol groundings being made with respect to a single specific human? And if you do that, obviously your problem won't come because this is the only guy who is going to talk. And so as long as you understand their meaning, that's fine. But that would make it very hard to get enough labeled data, for example, to ground. So you tend to assume that most humans will have common connotations for these terms. And then so you wind up starting with the grounding there. But then again, I normally consider explanatory interactions as a way of machine trying to change and the machine reconciling its model with the human. And previously, if the vocabulary was agreed upon in the first part of the talk, most of the reconciliation is being done in the context of making sure that the preconditions effects all match up. Here, actually, the grounding of the vocabulary might itself wind up increasing the interaction. So my answer, the long-winded answer to what your question is basically there would be enough commonality. That's how we are actually getting along. And then in specific terms, like for example, in the relative attributes case, faster versus slower might mean different things for different humans, but you are essentially doing that grounding with respect to the human in the loop. And so there could be some amount of tuning that is being done with respect to the specific human in the loop, even though I hope that much of the dictionary has been learned beforehand. That's what is happening in the scene graphs, for example.
That makes sense. Thank you.
Yeah, hi, also from my side, thank you very much for this great talk. I think you touched so many interesting questions, and I think not all of them are solved, but it seems like you solved half of them already. So thank you for that as well. I have two questions, but maybe start with the shorter one. So the last thing that you touched, if we notice that there is some vocabulary missing in the human, I mean, it is hard to find out if it's actually missing at our side or their side, but I would be interested if you have any ideas on how we could actually teach a new concept, name the new concept, whatever, right?
I'm sorry. Yeah, I mean, at the risk of, there is a paper for it. A student, one of my students actually just has a paper in the New Rips Hill workshop, which basically does this. And the idea would be that when you realize that the confidence is low for the explanation, then you are trying to generate more concepts that you're trying to expand. And so he basically provides a locally guided exploration of the concepts, and then whose grounding he will learn. It's still being done in online. It could be expensive, but that's a start of how you can get more vocabulary items from the human side, assuming that there actually is basically their vocabulary connects to it's their vocabulary that they do have a concept, you just don't know it. Whereas, as I said, in the second case, the AlphaGo case, that's the opposite one. So I think we just started doing like the beginning of it, where through this interactive vocabulary expansion, when the confidence is low. I didn't get a chance to talk about that paper, but I can send you a link to that. And that's our beginning part, of expanding by looking at we make some meta assumptions, such as, for example, the missing concept is close enough to the concepts that are currently sort of effectively, approximately covering the saliency region. I mean, I'm still talking about the machine itself is trying to, the mental model, I mean, the mental view that you can have is machine has this kind of a saliency thing, saliency map, either on a space-time tube or on an image, and it's trying to cover that region with the groundings of the concepts. That mental view actually is very helpful in coming up with making sense of how you would expand the vocabulary. And that's sort of starting from there, he essentially looks at close by concepts, for which there are actually, for which you don't have groundings right now, but you wind up learning groundings. So if it helped, but I can send you a copy of the paper that might give you.
For sure, that would be interesting. But so that also means that he could come up with new symbols that are basically made up out of already existing symbols that are with the closed concepts. Do I understand that correctly?
You could, although I think in the work that we are doing, essentially, so we are not, in our case, in this work, we are not combining symbols, but that is something that can be done. This is like the very first. So we had these as challenges, and we started like nibbling at the challenges. And the first one is essentially looking at the existing concepts that the humans do have and trying to see which of them would be relevant. And again, we kind of wind up using this idea that causally related concepts, concepts that are causally related to the one that is close enough might actually be helpful to find groundings for, and then you're trying to pick which of them is the best.
Okay. Yeah. Thank you. Very cool. I don't know. Yeah. Maybe you
yeah. Awesome. Well, so I have more questions, but I see that Katya is our next speaker is here now. So if anyone else has any other questions, we can take those real quick. Otherwise, we can just move on to the next speaker.
I just would have a small comment.
Yeah,
maybe if I can still go, because so I was one small thing, I don't know, not really missing, but from like an open challenge that I also still see in the areas that you're describing is still the multiple humans thing, where the robot actually doesn't play so much of an active role. So looking at the mental models between the two humans, right? Because even in everyday environment between the humans, there are these mental model issues, theory of mind issues or whatever, how the robot can actually play with these. You mentioned that you have something with multiple humans, but
so actually we have several of them, but the closest, given the tenor of your question, is an IROS paper from last year by the same student who is doing the vocabulary expansion. By the way, I don't know the names of the people who are asking, so it would be great if you send me an email afterwards, and then I can send you the links to the papers.
Will do.
This is one of the bad things of not being in front, because I could have then come and asked you, who you are, and so that I can, we give this talk so that we can, exchange this kind of information. So in Utkarsh is a student who has an IROS paper last year, which basically has multiple humans and then you wind up having, customized explanations in a scenario where, for example, one of them is a mission commander, one of them is a soldier, one of them is a surgeon, and the same decision will wind up having different explanations because they basically have different models of the task. This is something that we do support in that work. The earlier work, we basically, as I said, you can also provide conformant explanations, which are explanations that will work irrespective of a spectrum of models that you have. That was the ICAPS 2018 work. It still doesn't answer all questions about multiple models, but that was the parts that we have done.
Thank you very much. And I will write you an email so we can continue that. Thank you very much.
Yeah. Thank you very much. Let's thank the speaker one more time.
Thank you, guys.